In the last class, we briefly discussed. That if you have a sharp turn, sometimes called a cusp, it will have a different slope on the right side of this point and left side of this point, and that results in the limit definition of the derivative not to exist, and therefore you don't have a derivative at this point. Okay? Actually, I want to revisit that and tell you more conditions of differentiability. So my question is, we usually say if you have a smoothly varying curve at any point, we can find the tangent line, therefore the slope of the tangent is defined, therefore the derivative does exist, right? Okay, so let's try to think about why in this case you don't have a derivative and why in this case you do have a derivative, and what happens if the graph is not continuous. If you have a jump discontinuity like this, what happens? Okay. So we go back to the definition of the derivative f prime of a equal to limit h going to 0 of f of a plus h minus f of a over h. Okay. Now let's think about what happens to the denominator. Where does h go? 0. This denominator becomes 0, right? So in order for this limit to exist, what do you think the top should be? Or another way to say this is, what would happen if the top does not go to 0? What happens to this limit if the top doesn't become 0? Huh? Then you get some number over 0 and it diverges, right? So if you have a non-zero number over 0, that definitely diverges. For example, if you have 1 over 0, like 1 over 0 plus, that becomes infinity, right? So if you divide a non-zero number by 0, you get something that diverges to infinity. So the first condition that you would expect, just looking at this definition, is that in order for the limit to exist, condition 1 is not showing very well. Condition 1 is that limit h going to 0 of this top part has to be 0. Now for this to be 0, that means this limit has to equal to that. See, fa is just a constant number, so this doesn't change as h goes to 0. So this is same as just saying limit of h going to 0 of f of a plus h, and afterwards you're subtracting f of a. Here, like taking this limit is same as this because this part doesn't change. Which means limit h going to 0 of f of a plus h, if I move that to the other side, you get f of a. Now, is this obvious? Is this always true? It seems it's true. You just since you're sending h to 0, you just replace h by 0, and you get f of a. It seems like this should always hold true. However, it's not true, and you may feel a little bit more suspicious if I did a change of variables, a substitution. Just rewrite a plus h as something like, let's just say x is a plus h. Then as h goes to 0, where does x go? If h becomes 0, and if I say x is a plus h, where does x go to? X goes to a, right? So you have, if I replace a plus h as x, and I replace x going to a, I have the following definition. This comes from here with the substitution x equals a plus h. Now, if after this substitution I have this. Now, is this always true? The limit is equal to the value of the function. Is that true for all functions? No. When is it true? You've seen this condition somewhere. Continuous, thank you very much. This was actually the definition for the function to be continuous at a. So for example, if you had a jump discontinuity at a, let's say here's a, and let's say you have a jump discontinuity. The value of the function suddenly jumps at here. In that case, the limit of f of x, x going to a, is not even defined because the right limit and the left limit does not agree. Okay? Or even if you have a removable discontinuity like this, where the value is defined differently from the limit. Limit is this value, whereas the value is this. In that case, the limit exists, the value exists, but they do not agree. So this is not something that's guaranteed. Okay? It's guaranteed only if this original function is continuous. So you can rewrite the very first condition as following. We can just erase all the arguments I wrote here and just write down one condition that should hold first is that fx has to be continuous at x equal to a. So that's the first condition. Now let's think about what other conditions we should require. So first of all, the function has to be continuous, and that guarantees that this will be a 0 over 0 type limit. Right? This is a 0 over 0 type limit because top goes to 0 and the bottom goes to 0. Now, if it's a 0 over 0 type limit, does the limit always exist? Can you think about some examples? 0 over 0 type limit. Does the limit always exist? I mean, if you solve a lot of practice problems, you would know. You probably saw many examples where you have 0 over 0 type, the limit does exist. And you probably saw many examples where 0 over 0 type limit gives you something that the limit doesn't exist. I mean, there are a bunch. If you want me to name a few, for example, if you have limit of, say, x over sine squared of x, x goes to 0. Both top and bottom goes to 0, but the limit doesn't exist. Actually, the right limit goes to positive infinity, the left limit goes to negative infinity. Right? So that's one example. Even if the limit do not go to infinity, the limit may not exist. Here's another one. Do you remember what the right limit of this is? Positive 1. Left limit is? Negative 1. So the limit exists or not? The limit does not exist. Okay. So the second condition you should require, condition 2, is that the left limit, which is defined as h going to 0 minus fa plus h minus f of a over h, okay. Which is called the left derivative, by the way. This is the derivative where h is only taken from the left side. The left derivative has to equal to the right derivative. If they both exist and if their values agree, then we can say that this limit does exist. Okay. So to put this in words, the left derivative should equal to the right derivative. Okay, so these are the two conditions for the derivative to exist. If the derivative exists, it must have satisfy two things. It should be continuous, and the left derivative should equal to the right derivative. Okay. So therefore, there are three kind of possible cases when you pick a point on a curve. Okay. So here, this case here is when you have a point of discontinuity. Right? So this is when it's not continuous. Not continuous. What about this? Is this continuous at this point? Yes. But not what?
Differential.
Not differential. What about this one?
Yes to both.
Yes to both, right? Continuous and differential. Now, question, is there a fourth example where it's not continuous but differentiable? Can that happen? Is there any example where we have not continuous but differentiable? This is basic logic. I mean, if you're able to follow detective movies without a problem, you should be able to answer this question. We did all this analysis. Is it possible to have a point that is not continuous but differentiable? Yes?
If, like, the one point on the graph is somewhere else?
Like
if there's a line and a hole in the graph? Yeah.
like this one. That's a removable discontinuity. This is not continuous, and because the limit, well, I raised here, but this is limit of the function should equal to the value. That's the first condition. So this is not differentiable. Can't be. Why not?
Because it has to be continuous to be differentiable.
Right. So if the moment you say a point is differentiable, what does this condition say? It has to be continuous. So it's going to contradict the first condition if there's such a thing. Okay. That's just basic logic here. Okay. So think about all four cases that you can write about continuity and differentiable. Continuous but continuous and differentiable, not continuous and differentiable, not continuous and not differentiable, continuous but not continuous but differentiable. Out of these four cases, one case shouldn't be there. It's impossible. Which case?
Last
Not continuous and differentiable. That's an impossible case, according to the condition that we just put forth. That's very important. Can a function be continuous without being differentiable?
Yes.
Yes. Can a function be differentiable without being continuous? No.